Calculus BC, we are in section 3.4 and we are really going to focus on derivatives. The derivatives of trigonometric functions. Before we address anything, look at this star. You must be in radians. Everything that you're about to see here, the 6 derivatives of trig functions, it works with the assumption that your function is currently in radian mode. In other words, if we were in degrees, what you were about to see would not be true. We'll address that further on. Hopefully you've already seen this. The derivative of sine, well, it's going to be cosine of x. Look right below it, the derivative of secant is the secant of x times the tangent of x. What about the derivative of tangent? Well, that would be secant squared x. You're going to have these memorized. No doubt about it. Now, what you're seeing on the right-hand column, you can see these are co-functions. We have the derivative of cosine, and you can see that when we took the derivative of sine, we got cosine. When we take the derivative of cosine, we'll get the opposite of sine. When we take the derivative of cosecant, we'll get the opposite of, well, much like what you're going to see right here for the derivative of secant, it was secant tangent. Here you'll get cosecant of x times cotangent of x. You can see that there's some strong similarities between the derivative of secant and the derivative of cosecant. And then finally, the derivative of cotangent, very much like what you're seeing for the derivative of tangent, although look, you're going to say the opposite of, and then we'll have cosecant squared. First of all, a couple of things to help you. The derivative of co-functions like cosine, cosecant, cotangent, you're always going to have a negative out in front or an opposite of. It's super important for you to remember that. When you're looking at that first column here, we did not. But then you can see that these co-function derivatives are amazingly close to the derivatives of the trig functions without the co-functions. Hopefully you can see these strong similarities. You want to have these memorized. Make yourself flashcards if you need to, but these are non-negotiable. You really need to know these backwards and forwards. So, taking a look at number 1, take the derivative of this quotient of functions right here, and that means you're going to remember the quotient rule. The derivative of u over v is going to be low d high minus high d low all over low squared. So what we'll do just real quickly, getting this derivative out there, we can say dy dx right here. Dy dx is going to be low, which is 1 plus the sine of x, times u prime. Well, what was the derivative of cosecant? Well, you can see it right up here in the top right corner. It's negative cosecant x cotangent x. And then we'll say minus high, which we could say is cosecant of x. And then d low. Well, what's the derivative of 1 plus sine? Plain and simply, it's going to be cosine. Then down below, we'll have 1 plus the sine of x, that's our low function, squared. Well, a couple of things to point out to you. When you're working out a derivative here, I really want to encourage you to look for algebra methods like factoring. When I'm looking at that numerator, you can see that we've got our first part, and it looks rather messy, doesn't it, with these 2 parentheses, and we've got this second part over here. But there is something in common, and what I'm seeing in common would be that negative cosecant of x. Tell you what, I'm going to actually factor that out. And what's going to be left? Well, we'd have 1 plus the sine of x times the cotangent of x. And then I took away this minus right here, so I'm just going to be left with a plus. You can see already, guys, this has gotten way, way better. Factoring is so very, very, very helpful. Now, at this point, I do want to just clean this up just a tad. We're going to have our negative cosecant of x out in front. And as we distribute, you can see cotangent times 1, well, that's going to be a cotangent of x. But when I distribute sine times cotangent, and I'm doing this off to the side, please remember that cotangent is actually the cosine of x over the sine of x, meaning these sine of x's are going to cancel out, won't they? So we can actually just say plus the cosine of x. Look at that. And here's yet another cosine of x. So without too much work here, I think you can see where we're going. One more step to simplify this. We could say this derivative is going to have a negative cosecant of x here, a cotangent of x, but then we're going to say plus 2 cosine of x. And down below we'll have 1 plus sine of x, whole thing squared. And there you have it. One more problem. And this one, for example 2, we want to get the equation of the normal line. Now, please do remember that the normal line is perpendicular to the tangent line. Hopefully you learned that in AMA. If not, know it now. The normal line is perpendicular to the tangent line. You draw that at the same point of tangency, at pi over 3 comma 2 in this problem. But also, we want to recall that perpendicular lines have slopes that are opposite reciprocals. So, let's get to work. We can go ahead and say, well, y is equal to the secant of x. That means y prime, well, if we remember the derivative of secant, I hope right now you know it quickly and easily. It's going to be secant tangent. And by the way, if we were to plug in x equals pi over 3, we'd have the secant of pi over 3, tangent of pi over 3. We just have to review a little bit about our unit circle, of course. Pi over 3 is in the first quadrant. Down here is pi over 6. Up here is pi over 3. It's equivalent to 60 degrees, but we don't even need to think of it that way. I hope you know that the cosine of pi over 3 is 1/2, right? And you can also see this even by drawing a quick little triangle here. I hope you know that 1/2 is equal to 0.5, and radical 3 over 2, the other common value that you see in the unit circle, is about 0.833. But I guess what I want you to remember is cosine is always the x-coordinate. The x, which I have gotten red here, is small. That's going to be 1/2. 0.5 is a lot smaller, isn't it? So this point up here would be 1/2 root 3 over 2. Another way you could look at it. So that would mean, as we just said before, cosine of pi over 3, of course, is equal to 1/2. And likewise, the sine of pi over 3, of course, would be root 3 over 2. But look, the secant of theta is equal to 1 over the cosine of theta. So what's the reciprocal of 1/2? Well, it's going to be a 2. And tangent, of course, is sine over cosine. I hope you're well aware of. Right? So we've got sine over cosine. So that's going to be a root 3 over 2 all over 1/2. And Of course, what we can do immediately is just say, well, that's really like root 3. So we've got 2 out in front, radical 3. What is that? That's the slope of the tangent line. That's the slope of the tangent line. So what's the slope of the normal line? Well, we just saw over here, it's the opposite reciprocal. It's going to be not a positive 2 root 3, but a negative 1 over that 2 root 3. And of course, we've got our point given to us already. Here's our x1, y1. And writing this equation, I hope we can do this nice and fast. We'd get y minus 2. Here's a negative 1 over 2 root 3. Here's an x minus pi over 3. Gosh, that can look ugly. That can look really bad. It's fine. You can even add a 2 if you'd like. Don't let the radical and this pi over 3 intimidate you. The equation of a line, in this case this normal line, can have some ugly parts to it, but it's fine. Hope this is making sense to you. We're going to be doing quite a bit of additional work. Problems like we saw in example 1 with some quotient rules, maybe some product rules, and just some good general calculus practice. Good luck.